Thanks. Yeah, thanks for inviting me, Dennis and Stefan, who is not here. So I have a rather funky title, right? So the rise of tractable circuits from cryptography to continuous generative models. Actually, to disguise that, it's actually like a more honest title would be some nice work I did recently with circuits. So actually, it would be more honest title. And so I promised Dennis to not overstretch like the Star Wars reference here. So like just here, the force is strong in tractable circuits. Essentially, I want to motivate like kind of like why I find them interesting. So when I started my PhD, I was working with Bayesian networks and I had some great ideas like, hey, we can learn the Bayesian network by just constructing a bigger Bayesian network and like learn the parameters there. And my supervisor was like, oh, that's a funky idea, but like you won't be able to do inference in that. And like crap. So like actually back then I didn't really understand what we're actually really doing here. And I also like neural networks. And I thought, well, why aren't we like just learning that with a neural network? After all, it's just a function, right? With operational semantics, if you may. So we had some fun yesterday. And essentially, I was like always for the look or like looking out for something which is between these graphical models like probabilistic machine learning or like probabilistic models and neural networks. And 2012, I actually learned to know about some product networks, which are essentially like a special case of these probabilistic circuits. So in a nutshell, what are probabilistic circuits? They are representations of high-dimensional probability distributions. Probability distributions. And in some sense, like, yeah, I had also to reflect during my PhD, why is probability so important? In a nutshell, and I think this is really my big working hypothesis, and therefore I'm a probabilistic machine learner. Essentially, probability in a nutshell is optimal and consistent reasoning under uncertainty. And I don't know what AI is, and none of you really do, but so having like this feature, optimal and consistent reasoning under uncertainty, is like kind of like must-have in AI. So it's about halfway to AI to stretch it a bit. And like the cool thing is, well, this is cool, but like also hard. But however, as soon as you have a probabilistic circuit, essentially like many of the inference scenarios you are interested in are actually tractable. So you can do exact probabilistic reasoning. Therefore, probabilistic circuits, the force is strong in probabilistic circuits. What is also nice is that they really play well with logic circuits. And so in my perspective, so probability is actually just like a generalization of logic. The advantage of logic is, in my perspective, you can talk logic to humans, and sometimes this hard logical structure makes inferences easier than if you do like fully-fledged probabilistic inference. Anyhow, probabilistic inference is like actually like, well, generalizes to a certain extent like logical reasoning. And the third thing, which I also mentioned yesterday, is like they also play well together with neural networks, right? So like if you have a circuit, essentially it's a connectionist model, so you can actually plug that into neural networks or can plug neural networks into circuits. And we've done actually both of that in various modifications. All right, so what is a probabilistic? Shortly, so like, so I'm really in a luxury here that I don't need to really explain decomposability, smoothness, structured decomposability, determinism. It's really the same thing. Yeah, so like probably now all of you know these properties. It's really exactly the same things, right? So like smoothness means, right? So like essentially a probabilistic circuit has 3 units, leaves, the inputs, sum nodes, well, these guys here, and product nodes, well, these guys. Smoothness means like the inputs of sums, they all look at the same random variables. Decomposability means inputs to products look at disjoint sets of random variables. Structured decomposability, all the products with the same scope, with the same variable scope, factorized the same way. And determinism, at most one input to each sum node is non-zero, yeah, for each possible input. And really, what this is like really like kind of, if you are familiar with Gaussian mixture models, is like just like a deep generalization of that, right? So like, so here we have maybe a random vector x, and maybe we have split it in 3 blocks. And here we spend like maybe a few distributions just modeling this part. Here we have a few distributions just modeling this part. Here we have a few distributions just modeling this part. And this can be like Gaussian, but really you're not restricted in what distributions or densities or probability mass functions you want to use here. You can even use intractable ones, and I also have done that. I've plugged in VAEs here. But if you plug in something tractable, which means where you can marginalize, maximize, and whatnot, then the whole thing will essentially inherit tractability. Yeah? Not surprising. So products are really just like, well, together with the composability, this just means, well, I am a factorized distribution. I am a distribution over U and V, and well, I factorize in these two guys. Yeah, so like really just vanilla factorization of probability distributions, which means actually like a local independence. And smoothness together in some nodes essentially means, well, I'm just like a mixture distribution, right? So like Gaussian mixtures, a convex combination of densities is again a density. And really, so like this guy is a density, is a mixture of these three distributions. This is also a mixture of the same distributions, but maybe with different weights. By the way, I don't never draw the weights here on the edges, but essentially they exist, right? So like you take a convex combination of these inputs, and it's a mixture. And really, you just build up like deep structured mixture models in that way. Yeah? So that's in a nutshell what probabilistic circuits are. And then Tony was like, asking me to explain like what is the connection to logic circuits, and the best thing to do is like actually a meme, right? So like what's the difference between logic circuits and probabilistic circuits? So corporate needs to find the difference between this picture and this picture. They are the same picture, really. So if you're working with logic circuits, right? So like decomposable and smooth and whatnot, it's really easy to really convert that into probabilistic circuit, just to replace OR gates with sums, with weighted sums, yeah, convex sums, and gates with products. And instead of literals, you take probability densities down there. Yeah, that automatically allows you to convert logic circuits to probabilistic circuits. And people can write papers about that, like SDTs to PSDTs, right? So like in retrospect, it's like a cheap trick, but essentially you can do that essentially with any logic circuit. And the cool thing is essentially like this still stays compatible in some way, right? So like you can mix probabilistic circuits with logic circuits. Right, inference in PCs, right? So like if you're like more like a database person or like logic person, well, what means inference in probability? Well, as in logics or in databases, well, we're interested in queries, and we build up complex queries by concatenating or like by simpler queries or primitives, right? And smoothness and decomposability essentially allows you to do marginalization, so computing high-dimensional integrals or high-dimensional sums over your distribution, and conditioning, which really just is like using that as a subroutine. And the most general thing is like really sum over everything, so compute the partition function. Therefore, essentially in probabilistic inference, if you can pick only one, people would probably pick this one. So like it's essentially like some people even restrict or like would see marginalization being able to sum or integrate over your function as synonymous to performing probabilistic inference. In any Bayesian model, right, so like if you have prior over whatnot, and you have a likelihood, and you want to compute the posterior over parameters or other unobserved stuff, in essence, you're just solving a big integral there, so like a big intractable integral. So generations of PhD students actually have just like done that and like tried to approximate that. Yeah. So marginalization, conditioning, determinism also allows it maximization. So like it's nice. So like conditioning means I inject evidence about something, you update your beliefs, and then you want to get like the most likely configuration. So Yo Chang was yesterday doing that, right? She was actually telling you like how to first marginalize and then maximize. Well, unfortunately, that's like something intractable, and therefore Yo Chang came up with a good iterative way to actually find the global maximum. Structured decomposability or compatibility allows circuit multiplication, so the usual tricks apply here. Yeah, so like maybe just to illustrate, well, marginalization. So say we have this circuit, and we want to get rid of one variable m, which is contained in U, and allow me, right, so the output of this circuit essentially like the density over this whole random vector x, and we want now to get rid of this much of this one variable m. So that's essentially the semantic of marginalization. Get rid of something, account for this, right? So allow me to write this as like a little integral here at the sum node. Then I see, well, cool, an integral and sum commutes. So I can pull the integral down to products, right? So now this is an integral only over m. M only appears here and not here. You see like here, m is not contained here. So essentially you can distribute products, right? And essentially long story short is if you want to have this if you want to integrate one variable out of here, essentially you can integrate it out of here and leave the rest of that unchanged, which just means replace these guys with the marginal where you marginalize m out here. And it's like a trivial operation, for example, in Gaussians, but so essentially when you assume that you can actually do this here, therefore like the whole circuit inherits like this marginalization, yeah? So like this core routine of marginalization you can do, Scott, yeah?
Yeah, so I think there's some extreme independence here though, right? There are things that you can't represent, right? And because of that, you can exploit the structure, right? But almost it looks like you lose covariance, right? It looks like
Okay, no. Right. So I actually started, right, so like I've never seen a person, no matter how smart, and you're an extremely smart person, who's like really realized this automatically. Yeah, they assume independence, right? So that's what you mean, right? So like there's an independent distribution. But the point is like if you have like a mixture of independent distribution, that's not independent anymore. So
yeah, okay. I mean,
so
everything's a mixture of Gaussians, and we're happy.
Yeah, so essentially, like you have universal approximation if you take mixtures of Gaussians, even if they're fully factorized. This wouldn't be possible if this was not true, right? Essentially, like the picture I always draw is like, let's draw a Gaussian, right? So like if the likelihood equity lines are like axis aligned, then this means independence. So I have one Gaussian, this guy assumes independence because it's axis aligned. This one assumes independence, a mixture has correlation. So it's actually what's happening here is like that each of these sum nodes here is a discrete random variable, like in Gaussian mixture models, and like conditioned on this, right? So like this is actually a latent variable with 3 states, right? So like this guy randomly picks one of its inputs. Maybe then we go here. This guy picks one of its inputs and so on. So essentially it's a hierarchy of discrete latent variables, and conditioned on that, it becomes independent. But if you marginalize the C's, right, so then essentially everything becomes dependent. But, right, so like it's a conditional independence actually, right? So conditioning on all these decisions up there, this is like independent, yeah.
Yeah, I mean, I'm just wondering, for all practical cases, is this going to be a good approximate representation, right? I mean, I know people love mixtures, right? So I think for many cases it is, right? But where is it insufficient?
Well, I mean, it depends a lot on the actual structure, right? So like structure is key. You can also try to come up with like an over-parameterized structure. But so if you're familiar, for example, I mean, like in principle, this is like even complete factorization works if you have sufficiently many latent states, essentially. The Finetti's theorem, essentially, in principle. But you're right, it is important, and like messing up your structure will, not work too well. All right. Right. Okay. We can marginalize. And now let me advertise some cool work by this guy and he and Antonio from us and some other guys from last year's NeurIPS. So actually, what fun you can have with circuits, and like so like they came up with like this really nice example. So figure you have like this maps from video games, and you want to predict like the shortest path, right? And if you do that with deep learning, you would send it through a neural network, a convolution neural network, and then you'd say, oh, I have like one output for each tile here, and essentially if there is a path segment, then I put output 1, otherwise 0, just like binary structured output prediction. Yes, like if an image in, binary output prediction. And now you start train your ResNet 18 or whatnot with 1,000 and 1,000,000 samples, and all of them contain paths, right? So like you've labeled these shortest paths, and the ResNet essentially like optimizes its loss, right? And then you ask it a new image or test image, and then it tells you essentially like, this prediction, right? So like 1, 1, 1, 1, 1 over here, and like zeros everywhere else, which is essentially like a path, which means, oh, jump here, then jump here, jump over here, then jump here, because like crossing mud is like expensive, yeah? So essentially what the neural network did is like kind of get the right gist, but it just didn't realize what a path really is, right? And so why not tell the neural network, right? So like essentially the task is pretty simple. You have like this images input, you have a structured output object. So this is not a path, right? So like if you don't tell the neural network that it should output a path, it won't recognize this automatically. And essentially it's like, ChatGPT is great, right? And essentially like the big deep learning lie is that with enough data, you will fix this. Maybe, but how much samples do you really need to, all the samples were a correct path. How many do you need to really show them that the neural network understands really the concept of path without making a single mistake? And the idea these guys had, and actually it's a really nice and simple idea. So like from circuit perspective, it's like kind of obvious. From deep learning perspective, it is mind-blowing. So essentially like we can teach now a neural network what a path is, right? So essentially here's the structure. So like here they have the deep neural network that goes into a probabilistic circuit, which is kind of a structured distribution of bit patterns here, which may violate this path, right? But on the other hand, it's relatively simple to express what a path is in CNF, take that to a compiler, and this gives you some SDD, so some decomposable and deterministic non-negative negation form. And from machine learning perspective, this is just like, well, for any path, right? So like this Y here, so like any bit pattern, which is not a path, this will output 0, so doesn't violate the constraint, and otherwise 1. It's really just a binary mask, right? And you want to take that and multiply it on the output of your neural network. Essentially, you just like, if it outputs a non-path, you say, well, no, 0. If it outputs a path, then you say, well, it's a probability of a path. And if it is a path, you just leave it through, right? So you just switch off all invalid solutions by taking this product. Well, this was a distribution over all bit patterns. Now you've clamped something of that to 0. That's not a distribution anymore. You want to renormalize that. And the cool thing is, well, this is a circuit. You can still marginalize, get the partition function, bam, you divide. And therefore, you have now a distribution over valid paths given this input image. Yeah? And you train that with maximum likelihood. Nice, simple idea, beautiful, right? So, and essentially, well, you can guarantee that, now that your neural network just predicts like this correct solutions, correct paths. Yeah. Any detail questions? The authors are here, so for later. Yeah. Okay, and essentially, like, so I want to present you some nice application of that. So, like, side channel attacks in crypto systems is a master thesis of Thomas Wedenig. And essentially, like, the interesting thing is, like, advanced encryption standards, AES, right? So, like, it's actually like, it's a safe thing, right? So, like, you have like some plain text and some key, right? So, and essentially, like, that's an encryption algorithm which should like just like essentially encrypt your plain text and essentially give you a cipher. And if you have the key, essentially like an invertible function, you can like go back to your plain text. And it's in principle safe unless you execute it on a physical device, which is kind of cynical because you always execute it on a physical device, for example, your bank card or whatnot. So essentially, when you use a physical device, this physical device will have some leakage like power consumption, time consumption, electromagnetic emissions, heat emissions. So the crypto folks never get tired to like try new side channels, so artifacts of the physical device which performs your algorithm. And essentially, these artifacts contain information about what you actually want to hide. In particular, sensitive is the key, because if I get your key, then I can read all your future messages. And this is surprisingly effective. So here is like essentially like so the advanced encryption standard AES essentially works via rather simple computations. Essentially, like so it works with this 4x4 grid. So like these are bytes. You would start essentially like with your message and like XOR it with a key, right? So like essentially like with the key. And this is really just like permuting states. So so it's just a permutation of your states between 0 and 255. This thing, then you would like actually have like this shift rows. Yeah, so like essentially the whole thing just wants to have like an invertible function, but a complicated function so that you can actually scramble your information. You have essentially like something like a matrix multiplication modulo 2, and then you again XOR with the key, and essentially do this in 10 rounds or so. And then essentially after that, you have completely scrambled your plain text, and the invertible function is determined by the key. Yeah. That's essentially what's happening. So really, it's just like a bunch of computations which you can actually describe in logic. So here essentially, so like this is like actually the algorithm is repeated for 10 rounds, but typically what people do is like attack just the first stage of that. So here it goes in your key and your plain text. Yeah, you have a bunch of XORs. This is like scrambling your states, essentially, like, yeah. Then essentially here, and now you have this so-called mixed column stage, where you really just do a crazy XOR with all these inputs, so like 4 input bytes yielding 4 output bytes. The whole thing is invertible, but essentially like really just a scramble function, yeah? And in all stages of this computation, of course, your algorithm has like leakages, yeah, electromagnetic leakages, like indicated with these green arrows here. And what you can do is, like, if you have like the same device at home in your cellar, you just query it with a lot of keys and plain text, and you measure for conditional on each of these states here, or each of these variables, you measure essentially, like, you take a statistical pattern about these leakages, which essentially allow you to come up with a statistical model. So if you have a new leakage, you can get actually a good guess about what the state here is, yeah? Essentially just play a base rule, yeah? So like you have a likelihood, so a function for these leakages, which essentially allows you to give you a guess, a probabilistic guess about all these states here. Right, so like you measure this, and essentially also like at various other locations, and essentially you have like soft information about all these intermediate variables. You know how they are related via logic. Essentially, all you want to do is like distill this information, propagate it to what you want to learn, namely the key. And so like there's a state-of-the-art algorithm, Saska, and they are using so-called loopy belief propagation on that, so to infer the key. Yeah? So like they assume, so in this scenario, it's assumed, okay, you can actually see the plain text, and you want actually to learn the key that you can actually decrypt future messages, yeah? And you have like the statistical models, and it's surprisingly effective. It's scarily effective. On the other hand, so like a colleague of mine said, well, still this is pointless because like the biggest loophole is human stupidity, but still, since you can hack these things relatively easy, so with this side channel attacks. So just to give you a refresher about belief propagation or loopy belief propagation, well, essentially it's based on this classical graphical description based on a factor graph of an unnormalized distribution, right? So you have like random variables, you have like factors, like this means factor A is just like a function of these two guys, factor B is a function of these two guys, FC is like a function of these two guys, this is a function only of this guy. You multiply these factors, they are non-negative, which gives you an unnormalized distribution, and essentially I said marginalization is what you want to do. Either compute the partition function, so the normalization constant, or like get a marginal. And this is essentially done by distributing sums and products, essentially like pushing that into your factor graph. Essentially like, so like if you want to have the marginal of this guy, and there is like this sub factor graph, essentially if you have like the summation here, essentially it's just like a message which gets further propagated on a high level. That's what's happening. And this is an exact summation algorithm if the factor graph is a tree. But this thing here is not a tree, this is a scary loopy graph. And essentially what people do is like sending messages here like in circles. This has actually like no real guarantees, or like very weak guarantees. Does it converge? Does it converge to the true marginals? You actually don't really know, yeah? But you hope for the best, and it's like, well, if you do that here, essentially approximate inference with message passing, you can actually really guess the key nicely. So like the main idea is like now use this circuit technology. So like essentially like this piece here is actually just like a big chunk of logic. So like, and the idea is like, well, so like essentially it relates these 4 input bytes with these 4 output bytes. So can we just like make a big truth table, essentially represented as an STD, so as a logical circuit. And the surprising thing is like, well, you have like, well, 32 bytes. So no, so like you have 8 bytes, so times, hold on, 1, 2, 3, 4, 8 times 8, so like 64 bits, and you have like logical constraints, all these XORs. It was kind of surprising that, yeah, you can actually compile this whole thing. It's a circuit of like a few thousand nodes or whatnot. And now essentially what we've done is like we have now all these leakages. So like here we have this part 4 times, here this plate notation 4 times this stuff. We have like these output variables, intermediate variables, where you measure the leakage and get like guesses about these intermediate results. And they are now all tied with this huge high-dimensional factor represented as an STD. So the whole trick is by just like lumping all this together. We have now essentially like a tree, yeah, and we can actually do exact message passing. which in circuit language means multiply these guesses about your intermediate results, multiply it with the STD, and then just do exact inference over the key. So this was the plan. And yeah, ultimately it worked. But first of all, it did not really work. So essentially, like, you know, you have this relatively big circuit describing what the central logic, this mixed column is, yeah, which is already pretty big. And now you have essentially like, for each of these guys, 8, you have like a distribution over 256 states. And in principle, you just say, well, you just take the product, and the product is, so like essentially you compile all these distributions also in PSTD or like in circuits and multiply it into this circuit. So like to get like a big distribution over everything. And now the thing is now essentially you have like a product of 9 circuits, which essentially blows up. So it's like quadratic roughly, or like a worst case quadratic. But if like a growth, whenever you multiply, but you multiply 9 times. So like this really blew up, at least on the hardware my master student used. So the trick was essentially like to simplify like all these leakage distributions, right? So like these byte-wise distributions here. Essentially, we had 2 ideas, like let's introduce like independencies, then you get like smaller circuits. This didn't work too well. And then a very simple idea was that each of these distributions has pretty some sparse structure. So essentially, many of these values essentially are close to 0, so we just set them to 0. So we just took like the 1 minus epsilon portion of the probability, set the rest to 0, renormalized, and this yielded way smaller circuits, which you could actually really multiply in and actually do exact inference. And the thing is, well, this actually set, at least on this toy problem, new state of the art. So essentially, like this is really like what crypto folks are doing, Saska based on belief propagation. And here, yeah, so the success rate essentially like is measured. You get some ranking, so like whenever the key is among like the top K ranking, then you call it a success. It's measured in some weird way. So long story short, essentially by essentially approximating these leakage distributions and doing exact inference, we actually were able to outperform like this this state-of-the-art message passing based inference using exact distributions. So we had to approximate slightly, but then performing exact inference essentially like gave you quite some improvement here. Yeah. All right. So yeah. So yeah, I also I recently started a project on DNA storage. So essentially like using DNA to construct a so-called structure and then essentially like imprint information there, essentially like a DNA CD, ZD compact disk, and essentially like you have to use computer vision to read it out, and then using some error correction, again some piece of logic. The idea is like really like to just incorporate with this neuro-symbolic circuit approach directly the error correction in your visual recognition system. So this is actually, we haven't done this yet, but this is the plan. Yeah. So not a funky application of circuits. Are there maybe questions about this crypto side attacks? Or
so could you say a bit more about how is the success of your algorithm measured actually? Like
okay.
Right? I mean,
Yeah. So
you cannot get a beat, right? I mean, there is no way that
okay. So like essentially, yeah. Right, so like essentially, while you have all these leakages, distributions, well, given leakage, what is the distribution of this intermediate result? You glue that all together with the logic, right? So propagate essentially the information to the key. Now get the distribution of keys. And now you have essentially like most likely key, second likely key. Essentially like you list up like them, and you say have a threshold, something like a threshold, where you say if it's among the top 10, right? So then essentially like your attacks are like you try the first 10 keys or so. If you have a hit, then it's a success. Otherwise, not. It's a little bit more, but roughly along these lines. So it's like, have you actually guessed among the top K candidates the correct key? Roughly along these lines. Yeah. But, details in the. Yeah.
I mean, like chosen at random. Actually.
Yeah. So like the assumption here is that a priori they are uniformly at random. Yeah. So otherwise, you would the problem would be easier, right? So like yeah. Okay. So another line of research is we've recently started is like how to connect continuous generative models with probabilistic circuits. So to motivate this, there are a lot of generative models in the machine learning community. You've probably heard about GANs, generative adversarial networks, variational autoencoders, energy-based models, normalizing flows, autoregressive models, and whatnot. So and PCs. And essentially all of them, they want to achieve the same thing. They want to model a distribution over data. And as said, so what you want to do ultimately with a probability distribution is performing inference, right? So like you want maybe samples, you want density, evaluation, marginals, conditionals, moments, maximization, expectations, whatnot. And like the poor thing, so where PCs really shine is that all these funky mainstream generative models, actually they cannot do that, right? So like they all fail at marginalizations and other inference routines, and PCs can actually do that. On the other hand, they are way more general or like way more flexible typically and like more successful in data fit. Yeah, so like they produce nicer samples, they produce higher likelihoods. Yeah, so essentially there's like a gap, and the gap can be explained via the tractability expressiveness lemma, right? So like PCs have like stronger assumptions, and therefore like you are less flexible. Your hands are a little bit tight, right? And essentially like you have this tractability expressiveness dilemma. Although I'm not really sure where we really are in practice. Like theoretically, this is clear, but in practice, I'm not really sure whether this is like really the main source of why PCs are a little bit subpar to these other models. Another idea, and this is like actually linking to this continuous generative model thing, is all these successful things like GANs and VAEs, they are essentially like so-called continuous latent variable models, and the PCs are essentially like discrete mixtures. So, and essentially it's like kind of an intuition that this might also play a role here. So essentially a discrete mixture is really just like a convex combination of densities, right? So like you can also interpret this as a latent variable, yes, like as a discrete latent variable, which has been marginalized from the model. Typical examples, Gaussian mixtures, PCs, they are typically tractable, so you can actually perform inference. And all these nice, funky machine learning-based models are essentially like, can be understood as continuous mixtures. So essentially you have like a simple base distribution, prior distribution, mixing distribution, which is typically something like a white Gaussian. And you have like some neural network representing a conditional over X given C. So in the VAEs, you would output like a simple Gaussian, which those parameters depend highly non-linearly on C, so like this latent code. In GANs, essentially like the same. Flows have also like the same idea, but with transformable, with invertible transformations. In the end, essentially what you do is like having this big integral over C, which makes the whole thing highly intractable. So like a high dimensional integral is a computation nightmare. So all these models are like essentially intractable. But, and this is like actually like the insight we wanted to follow, they all connect the latent code and X in a continuous way, right? So like if you have a neural network between X and maybe the parameters of between Z and the parameters of X, or like the distribution of the parameters of X, or like in GANs directly relating X and Z via some continuous transformation. And it's kind of, you could think that this has to do with like their generalization properties and essentially why they work better in practice. So essentially the motivation here is like, can we get best of both worlds? Can we have like PCs now also with continuous latent variables or so-called integral nodes? And really this was like I guess like really the main motivation of us, like, oh, we have some nodes, we have product nodes, we have distributions. Can we have integrals? And essentially what would that even mean? And essentially like the most natural thing here would be to have like a continuous latent variable in your PC. But we are fans of tractability, so can we still have like essentially tractable inference, right? So that this seems like to be in conflict because high-dimensional integrals are hard. Except when they are not, or like when they are essentially, so like continuous latent variables models are like this integral here. If the latent dimension, right, if C is like just one-dimensional, right, then I have like a one-dimensional integration problem. Well, you can just shoot at it with numerical integration. Or like if C is like sufficiently small, then you can actually still apply numerical integration like quadrature rules and essentially like make this like morally tractable, so to speak. And also what is interesting, right, so like all these quadrature rules essentially approximate this integral with a weighted sum of this integrand. So like you pick like integration points and like weights, but essentially you replace this integral with a sum. And this is also like, as a PC person, you say, hey, it's a sum, so we're back in PC land, right? So essentially interpreting numerical integration schemes as, again, as a sum node, which is like interesting, right? So like if you have this continuous variable model, but now you approximate it, which again gives you a sum, which essentially means, oh, I have a neural network in here, which is a weird way to parameterize my model, but the actual inference machine brings me back to a standard PC. Those parameters are essentially given by this continuous model here, essentially. And yeah, so essentially, like, yeah, so there are now 2 papers. So like the first one was, let's have a continuous variable model. So like essentially using a PC. So this would be just a PC, depending now on a continuous variable with relatively low dimension. And similar as in this other funky machine learning-based models, this is like, again, like a low-dimensional white Gaussian prior. And essentially like this model here, x given c, so the is just determined as follows. Like the parameters of the PC are essentially governed by, the parameters of the PC are governed by c, this latent code, via some neural network. Yeah? And yeah, so we used even pretty simple PC structures like fully factorized or like a simple tree. But which now depends like in a continuous way on this latent variable. And it was kind of surprising that even this simple structure actually set new state of the art. So like comparing to the best standard PC, and essentially like these are like our methods and they are so like variations. So like this is fully factorized, this is with this tree structure. And this is like, well, some other hack or like other technique, essentially like setting new state of the art on these 20 binary data sets. So we were talking about benchmarks. In PC land, this is kind of our benchmarks, and they are not that great. So like I call them sometimes the 20 terrible data sets. So,
Use these in 3 years.
okay, yeah. So plus for he. Yes, very good. Okay.
I just lost context. You talk about continuous integration, right?
Yeah.
Binary data sets. I'm not. I'm missing.
Well, the latent variable is continuous. But the x is the data is binary.
Okay.
Yeah, so you can essentially So essentially, like it's about the latent variables. So in PCs, normally the latent variables are naturally discrete, and like the big conjecture here, and like we wanted to play with integral nodes. That was the real reason. But can we have continuous latent variables? The leaves are really not a problem. You can use discrete, or like leaves over discrete data or continuous data. The leaves are not a problem. The axis, you can pick whatever you want. The latent variables are essentially naturally confined to discrete hierarchies of discrete latent variables. Now we have continuous ones, essentially like a continuous latent variable over discrete data. Yeah. Okay. Also, like the samples look nicer, right? So like right here. So like, and essentially, I think like the main motivation for Alvaro was like to put this in here because like these are samples from the models I developed, which are really looking like kind of shitty. And like, so like these new continuous variable models produce way nicer samples. And then essentially we recently followed up, right? So like the first idea, so like this first idea was just like having a PC. Both parameters are governed by a small continuous latent variable. But what we really were striving for is like really build that into the structure in a more intimate way. And essentially like a recent follow-up work with Gennaro Gala and Cassio and Antonio and the supervisor, Eric, the supervisor of Gennaro. Essentially we thought, well, can we do more? Can we have essentially like something like a latent tree over continuous variables, and essentially like they govern essentially like these observables. So having essentially like a PC structure, it is now essentially like a new kind of language, so to speak. Essentially, it's like using standard PC language, sums and products, but interleaves like this integral nodes with the semantics, so to speak, that you have like always a continuous latent variable in here. So whatever is below depends on this latent variable. And essentially, you have like message passing, you essentially need to integrate along the way. So if you use like maybe Gaussian factors here, you can actually do that like analytically, pretty similar as in your work, right? So like doing like stuff analytic, but again, here we used numerical integration. And if you're careful, essentially like you get essentially, again, something like an inference machine for this semi-continuous PC or like a PIC, probabilistic integral circuits. Essentially, you can again spawn it back to a standard PC with a lot of sum nodes. Those parameters depend on these continuous factors in between here. Yeah.
If the parameters lower down depend on all the latent variables, don't you get another high-dimensional?
Well, So in the paper we just submitted, so like no, you have like essentially you have like a tree structure. So like you need to respect this tree structure here. This is so like this latent variable only depends on this one, and this becomes independent of this one given this one. So you obey this like this independent structure here, which is not shown here. So yeah. So I think we are not yet settled on how to like represent this on a higher level, but essentially, yeah, we have like this independent structure here. Yeah.
If you do high-dimensional integrals, I mean, I'd say more complicated Monte Carlo, right? And in fact, my students, we got a rejection at some point, and the reviewer said, you should try Hamilton Monte Carlo on this neural net.
Yeah.
And we did. It was annoyingly effective, right? So yeah. I would mention as an alternative, right? You could just go full MCMC. To deal with
right, yeah. You can do that. You can essentially do a lot of things. You can do analytic, you can like do numerical integration, you can do sampling, you can do variational, you can do all kind of inference scenarios. True. I think one motivation why we want to do that is essentially, you know, in probabilistic machine learning, everybody's doing either sampling or variational. And if you ask, well, where are the guarantees here? They are actually, well, good luck with coming up with good guarantees with sampling and variational. There are essentially none. And it's not really easy in numerical integration, but at least if we get like, right, so like the integration bins are essentially like the number of sum nodes you spawn here, right? So like essentially like you have, this is our model, and you can essentially design how fine-grained your inference machine is, which means you get like more and more sum nodes here. And at least with the theory, if you use enough, then we get, so like, and in principle, we can derive bounds. It's not easy. It depends on like these factors in here and the Lipschitz constant and whatnot. But in principle, we can derive that in an easier way than with sampling. It's like one of our motivation that we can actually derive bounds here. Yeah. So for the sake of time, so like Antonio really wanted me to show this image, but I won't explain it for the sake of time. So yeah, really, it's yeah. So these are integral nodes, and like yeah, this is like our inference machine based on numerical integration. Like we get a lot of sums. Here, these are like the neural networks we use between latent variables. These are the neural networks which we choose latent variables and observables. And essentially, like we'll get an approximate likelihood we use trained with Adam. Okay. Yeah, this is interesting though. So like essentially like illustrating when you use like a standard discrete PC, right? So like essentially like this dependency between like latent variables typically don't have. So essentially, the idea here was like so our inference machine essentially is again like a standard PC. We just like give this free parameters and learn this. You get like this, essentially no structure. If you have this continuous factors, you get essentially like this nice dependency, which is maybe interpretable, maybe not. You have the feeling that essentially like this latent potentials here get essentially like something like a interesting structure. And yeah, again, state of the art, so essentially like here, more or less. So if you're here, so like these are like standard PCs. Here's our stuff. Essentially, if you're here, then our stuff wins on a wide benchmark or like on a big benchmark, m-distant variations. Yeah. Right. Yeah, I think that's about it. So thanks. Continuous variables in PC? Seriously? Yeah.
Right, let's take the questions to the coffee break.
Okay.